So we're going to talk. Hi, I'm Rob Shakir. This is Carl Lebsack, both from Google. We're going to talk a little bit about some work that we've been doing in the wider industry and within Google on getting rid of SNMP and replacing it with streaming telemetry. And we'll try and go through a few of the problems that we've had, and then Carl will talk about some of the actual implementation that we've done. Throughout, we're going to try and use some data from our actual network deployments of the protocol. So the problems we have with SNMP are numerous, and I'm going to catalog a few of them, but this is really one of the key ones. We don't have any kind of source timestamping in SNMP. So when we're doing things like producing rate calculations, then we don't really know when the data that we're calculating based on comes from. We know when we made a client request, but we don't know when the device collected that from the underlying data source. Now, in multiple different devices that we work with, there's multiple levels of caching. So really, we end up calculating these rates based on some unknown time and kind of guessing. Now, these graphs show the impact of that. So on the left-hand side, you have the graph from SNMP. It shows instantaneous rate rises. It shows rate spikes that our graph on the right doesn't show at all. Our graph on the right shows traffic smoothly increasing and no spikes on the far side. And this is one of the sets of artifacts that we get from having SNMP as a data source in our networks. Now, those two graphs, you might look at them and say, oh, you're being kind of picky. They look very similar. When we start to look at what really happens at any kind of load in a real system, then this gets much, much worse. So the left-hand side of this graph shows SNMP data from an interface. There's multiple spikes. Apparently, we've worked out how to put terabits of traffic through a 10 gig interface, but just not that consistently. This shows where we're unable to rely on this kind of data for making real control decisions based on the network. We're having to guess what's right in terms of the data because there's so many artifacts in it. And this will lead you to do things like moving average windows over longer time periods just to be able to smooth out these artifacts. The right-hand side of the graph shows when we've turned streaming telemetry on. And this is the same device, the same interface, and this is the breakdown of traffic at the time. We can see that it's smoothly evolving. It's actually accurate to the underlying data source of what's happening in the network. So the key problem, SNMP just doesn't scale. For systems that we've seen built during 2017, 2018, modern systems, we still can't scale them over 1/10 of their full interface counts and pull data at 30-second intervals. We get SNMP timeouts, so we're not getting data back within the polling interval that we have. The problem is here we want data on the granularity of seconds. We want fidelity of the data to show us what's happening in single-digit seconds. And the reason you might want that is if you look at a graph that's something like this, you've got a traffic source. The traffic source is spiking. The blue dots show us sampling it via streaming. The red dots show what we can do via SNMP. And essentially what we can see is that there's these spikes that can be picked up if we sample every 2 seconds, whereas the data that we're getting from SNMP is 2 orders of magnitude out. So this gives us no way to be able to root cause this kind of issue. We might be seeing loss on this port. We might be seeing issues with applications over it. But the data we have with SNMP just doesn't really give us any insight. So that gives us a set of things where we're looking at data sources that are sampled, they're counters underlying on the system. But really, we also want to be able to get events from our network. We want to know what's happening in the network, some of the automated mitigation that we want to do. We need to know what's really, really going on. Now, we end up with this tension here. We end up with a tension that says, if someone wants to know what's going on in real time on a device, then you poll really often so that you don't miss any events. Now, the problem for that is that devices, to be able to scale, really want less pollers. They end up building caches if they have to go and pull these data sources asynchronously when they don't really know when a request is coming in. So we want to do something like design a system that gives us an update in a second after an interface goes down. And we have 3 choices today. We can poll every interface every second, but we've already shown that really even at polling at 30-second intervals, we can't scale. We can run with SNMP traps. The problem with that is they're unreliable. So we end up saying, oh, well, we don't really know if we got the notification to say that the interface went down, so we'll have to go and poll it anyway, which doesn't work. So in this work we've been working on, we've also focused on being able to push events reliably through the system so that we know that when something happens in the network, we're able to get it through a low latency, reliable channel to know what's happening in the network. So that's the existing data sets that we poll. If you look at what we're doing with more and more as we build systems that are hybrid between things that are running on a device versus off a device, well, we design whole new protocols. We design BMP. We put IGP data into BGP because we want different ways to be able to take data off a device. And that means that we're pushing a variety of different clients to be able to consume data from the network. It's increasing the complexity of the overall system because we've got this protocol that doesn't scale. If we want to look at things like routing table data, there's orders of 2 or 3 orders of magnitude larger than the other data that we're pulling from devices today. We're already in a scale problem. We already can't get the fidelity that we would like. And we're trying to introduce this kind of data into the protocol. So we've been working on this system. It's open source. It's been with a collaboration between vendors and ourselves and the wider community to develop a technology that's called streaming telemetry. What it is it's source timestamped so that we have that accuracy. It supports being event-driven, so things that need to be pushed as events can be. It's subscription-based, so it's a publish-subscribe model. And it gives you a way to have a system that's eventually got an eventually consistent view of the state of the network off of the network. This is all developed together in a set of open standards. So there's the main one of which is the gRPC Network Management Interface, GNMI, and it's part of OpenConfig. So not only have we thought about the interface to the devices, we've also thought about the data model that the device is pushing and how that has to work with the telemetry that we want to push from the network. So I'm going to hand over to Carl, who's going to talk a little bit about our implementation and some of the more technical details.
Thanks, Rob. And so the first and biggest point we want to make is this isn't just a science experiment. This isn't something we're trying to market and sell. This is not slideware. We've actually started to deploy this at Google. We have 30% of our production vendor devices have moved over to streaming telemetry, and we're actively displacing our SNMP monitoring continuously. We're already at millions of updates per second, and we're going to see this continue to increase. We're also going to see it decrease, and I'm going to talk a little bit about that later. But this is something that we are actively deploying and are trying to work with vendors to try to make this more robust and a good solid replacement of the legacy monitoring systems that just are no longer serving us. I really want to talk about how streaming telemetry is more efficient, and Rob hinted at this with the event-driven model, but we're kind of flipping everything on its head from SNMP being a pulled model to a push model, where the device is actually originating the data, because that's where the change is actually occurring. And so we want to switch this so that the device is actually scheduling the delivery, and this is one of the ways that we get the efficiency. First, the device can, since it's subscription-based, it knows up front what data is going to be collected, and therefore it can schedule the most opportunistic way to get that data, and it can batch collect it from the sources where there are opportunities to do so on the hardware. It doesn't have to worry about being asynchronously pulled by SNMP collectors and not knowing what's going to be in that payload prior to its arrival. In addition to that, it can also batch send to multiple clients. In a deployed network, we actually have multiple SNMP pollers in our legacy system just in case one of the SNMP pollers goes down. And therefore, you have 2 asynchronous clients that are not necessarily in sync with one another, and therefore the device has to employ those caches to be able to handle those requests. In streaming telemetry, if they both issue the same subscriptions, the device is going to know that, and it can therefore, when it batch collects this data, it can batch send the same data to multiple clients. And so it's not having to try to fend itself off from a bunch of asynchronous requests from any number of clients. The other thing that we want to talk about is event-driven. We want to push the data as soon as the data changes. And so in that example before where we talked about interface state, we'd like to know as fast as possible when an interface goes down. However, if the interface is not going down, we don't need to know that it's up, 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 up on an every second basis. And so what we'd like to do is we'd like to eliminate all of that unnecessary traffic that we would get with a poll model where you have to repeatedly ask. And so what we want to do is we want to establish a persistent connection to these devices and use that like a heartbeat where we're getting updates about other things that are changing and not having to send the redundant data for things that don't change. The other thing is if we do this and we switch to push only when the data changes, we can actually drastically drop our throughput and still get this extremely low latency. Now I want to kind of divert a little bit and talk about the implementation and why we picked gRPC as the transport. One of the things based on TCP, this is a connection-based protocol as opposed to SNMP, which is UDP, which we heard in the last presentation that there are other problems with UDP. SNMP was on that attack list vector that you saw. One of the things that you get once you move to a connection-oriented protocol is this ability to have the event-driven telemetry, where only the changes are necessary to be pushed, because you know if the connection is up that you have a live connection to that device. And you're getting an implicit heartbeat from the things that are changing, and there are lots of things that are changing on the device all the time. And so there's a huge data set on there that doesn't change very often, but you would like to know as soon as it happens when it does change. The other thing is gRPC offers us the ability to run over TLS. The internet of plain text is no longer. Table stakes today is to have encryption, and so we're relying on a newer protocol that allows us to be able to encrypt from day one in this particular implementation. The other thing that we've decided to do is use protocol buffers, which we are Google. We have used protocol buffers for a long time for everything. But one of the things that's really, really nice, we don't have to go and invent new serialization protocols to worry about cross-platform compatibility. gRPC also has a really nice mechanism for being forward compatible to add new data sets if we want to change the protocol slightly. Servers and clients don't have to be on exactly the same version, and it offers that kind of ease in transition. Now, one of the things that's really, really nice about SNMP is being based on UDP. If there is congestion in your network, the traffic just gets dropped, no big deal. Now, for switching over to a connection-oriented protocol, the thing that you might worry about is, what if I'm trying to push data to a client and I can't get it out there as fast as I'm trying to push it because we've switched to a push model? We're going to run into congestion, and you can imagine that if you're trying to queue up all of the data that has changed for a client and it just can't receive it fast enough, and there could be a couple of different reasons for that. Either you have some network congestion between the server and the client, or somebody has written a poorly performing client and is just not receiving data very fast. Your catastrophic case is they establish a connection and never receive anything. You really want to be able to kind of protect against that. And in TCP, if you have guaranteed deliveries, like what do you do? And so we need to figure out how to handle this particular problem now that we didn't have to do with UDP. And so what we're proposing is to use an application level queue coalescence mechanism. And I realize that this slide is a little bit detailed. You don't have to take notes or snap a picture or anything. We have an open source implementation, which I'll be talking about in the next slide. But the key points is we detect the back pressure from the server side with blocking send and gRPC. And so at some point that you're not going to be able to queue up any more data. You're going to see a little bit more pressure on the send. And if you have incoming data from whatever your underlying sources are, that throughput is not going to be able to be met on the output. And so what we want to do in that case is not queue up the old stale data, because in a telemetry system, ultimately we want is a real-time view of what's happening. And so in those cases, we'd like to, on a per data set basis, keep track of the keys that have changed that are destined for that client. And if you get an update for a key that is queued but hasn't been sent, you actually want the newer data instead. And so what we want to do is be able to dump this old stale data, similar to what would have happened in SNMP, but we want to do it selectively such that eventually, once the congestion clears, or even if it never clears, you always have a roughly fresh view of what's happening on your devices. And a critical event, like an interface going down, is guaranteed to be delivered still. And I'm going to talk a little bit about the open source collection framework. We actually published CLI for the GNMI probably about 9 months ago, and we've had several of our vendors who have been testing with it. Just this last week, we actually open sourced a caching collector. This is something that supports GNMI on its input from the devices, but also GNMI on its output. And so if you're looking at how would you do a GNMI implementation as a server, this is actually both a server and a client. And so this is a reference implementation that kind of illustrates some of the things that we're talking about today. It can collect from multiple GNMI sources and aggregate them together. So if you have N devices and you want to gather those statistics in one place, you can do that with this particular collector. It supports multiple GNMI clients that can actually get subsets of the data. It uses the same filtering protocol that GNMI supports and prescribes. It allows you to get things just kind of once-off polling. If you have some legacy system that just isn't designed for streaming, which none of them are because nobody thought about this previously, apparently. Everything is based on SNMP. And so if you need to be able to plug that in, there is the ability to poll the front end of the system and get that data. It also allows you to actually separate your client directly from your device. As Rob mentioned, one of the previous problems is In SNMP, if you try to create some sort of aggregation of SNMP data, just because you can't pull frequently enough, you get a lot of clients that are just upset, and they decide, I'm just going to go directly to the device. I can't rely on some caching infrastructure. In this particular case, because the caching infrastructure is streamed and is almost real time to what the device has itself, these clients can actually rely on it, which means that you can restrict accesses to your device and not allow end clients to go directly to them. It helps you more reasonably manage the load on those devices. Now, there is a little bit of a chicken and egg problem because GNMI being new, day one, we didn't have 10 implementations to test because nobody had implemented it before it was designed. So what we've done is we engaged with our vendors fairly early and tried to get them to propose anything that they could stream data off the devices to us. And so we had several implementations early on, and what we did is we iterated on the GNMI protocol, and we built a layer of what we call proxies that translate that data from whatever format they could give us into what we would like it to be in GNMI. And so we've gone through a fairly painful churn of iterating on this to be able to come up with something that we think will hopefully stand the test of time and allow us to migrate the whole industry to a new model for being able to have a standard way of getting telemetry off these boxes. But this is a process that we have gone through, and this is actually the model that we're in the middle of deploying, and we're gradually going to be peeling away these proxies as we get full support for the OpenConfig data model and the GNMI implementations. And today, there are at least these vendors, these are the ones that have given us permission to mention them in the context of this presentation, who have either in released code or EFT firmware images have an implementation of GNMI. And so not just the early versions that we were working with to iterate on, but actually are trying to support the GNMI full protocol. And I'm going to leave it on this slide. This is where I've got links to the general OpenConfig Net project, which talks also about the data modeling as well as the protocols. And we also have the link directly to the GNMI repository on OpenConfig GitHub. I'll turn it over to questions. I see we have one here.
Julian Luchek from Juniper. Rob, in your part of the talk, you alluded to the fact that you're using the streaming telemetry to trigger automated mitigation. Can you elaborate on some of those automated mitigation use cases?
Probably not, no. I can talk to why the general system. So we have approaches whereby some of, and we talked a bit about it in an Espresso paper that we published last year, where the subset of the routing functionality runs on the device and subset runs off in our own stack. And for that, you clearly now have lost the ability to couple the routing elements into signals in the system. You know, usually you'll have some way to be able to get interfaces events as a routing protocol. If you're not on the device, then you don't have that. So that's really our primary cases where we're looking at things, as well as, you know, kind of repair automation and the same kind of things that the folks were talking to earlier, where to be able to hit the availability that we need of networks today, we just can't involve humans. So this framework for us is really a way to push towards both enabling those off-box control things as well as management plane operations that fits in that kind of wider framework.
Yeah, on the alerting as well, I'll just mention that Rob mentioned we have to have a very long time window of averages on SNMP to kind of get rid of those artifacts. You can't trigger alerts on edge-triggered events in SNMP because you can't calculate rates accurately. If you can actually get good rates out of your system, you can actually fire your alerts more quickly and at least instigate humans looking at the problem earlier as well. So.
Hi, I applaud anything to get rid of SNMP. Have you ever looked at DDS, which is also another pub sub, which goes after hundreds and thousands of millions of devices? Are you familiar with that? I think it stands for distributed data streaming, something like that.
There are several pub sub mechanisms that we were looking at early on. One of the things that most of them do that we don't do in this system because we're so low to the network is worry about persistent storage. We're most worried about efficient delivery of data that is extremely fresh. And so in this particular collector that we've released, there is no storage mechanism. And the way that we deploy this internally is we store it by making a copy of that stream post this delivery mechanism. And so a lot of the pub sub systems have guaranteed delivery of like every message. And in this case, where we want to have that coalition, where we want to be able to discard things, We want to make sure that the data that is arriving at a client is as fresh as possible and not necessarily have a guaranteed delivery of every single event on a particular data. So like if an interface is flapping, really you only want to know once it stabilizes, make sure that you have the last state. But if it's flapping so fast that you can't deliver every single change, the interim ones, the transitional ones are not necessarily as important. Oh, another question?
Hi, BJ Hoskins from Sprint. If you were building a greenfield network today, would you say it would be feasible to do it with streaming telemetry exclusively for the operational aspects of it, or are there still some gaps there that would have to be filled with SNMP?
No, I think that it's possible to deploy entirely on streaming. So the general rate of progress, we went through a lot of iteration up front. We've gone through a lot of design with vendors as to fitting things together, and now I think there's fairly good implementations everywhere. Really, the problem that you have is like, what data set do you want to take? We kind of decoupled internally the implementation of the protocols and getting the data off the device to the schema that was being used. And that's meant that we've ended up with these proxies doing translations. So to adopt it straight away, you probably don't get a vendor neutral data model, but you do get a vendor neutral service. There's partial support across different vendors for the vendor neutral data model, but some you would probably have to infill some gaps. And particularly, there's been a lot of work with vendors to look at how they sample their underlying data sources and how they get it onto the wire efficiently. So we've been through lots of iteration, even with vendors and kind of native schemas, that when we start to look about how do you transmit that, it just doesn't scale. But I think right now it would be possible to build something with Greenfield, and we've actually introduced vendors like that into our network.
Thanks.
Go ahead.
Hello, Tony Tauber, Comcast. So with old data, SNMP gathered data and the new data streaming gathered, any lessons learned that you could share about, kind of viewing those things together, like how to impedance match them so that you can sort of make sense of something, gathered the two different ways?
Sure. One of the things that we've done is we've got a bunch of clients internally that are relying on data that has been collected from SNMP for a very long time. And that's kind of the persistent storage layer that I mentioned earlier. And so we're replacing the delivery. One of the things that we've chosen to do is try to maintain a backward compatible layer at that storage. And so we're basically turning everything so it looks like it were SNMP OIDs. In order to kind of meet that equivalence bar, and then we're going to move everybody down once we've kind of got ubiquity. One of the things that we see is that many of the data becomes cleaner when we switch it over, but we're still gathering that data at 30 seconds in those persistent storage mechanisms, just because it makes it easier for clients to not have to deal with disparate timescales. But we're looking to continually improve that. But that's one of the things that we've done, is trying to actually maintain backward compatibility in the way that we're presenting the data if we have a legacy system.
And right, so I mean, that was my thought too, but any gotchas or caveats or lessons that you can relate?
I think that side of things has been relatively painless, actually. I would say that it's actually been a big advantage to have that norm. A few bugs accepted, but
well, no, I was actually going to say that the biggest problem that we've had is the poor quality of SNMP data to begin with, and actually selling people on the fact that your data is now better and actually qualifying it. One of the things we've had to do is run through a bunch of tests that compare the SNMP data to the ST data. When you know the SNMP data is wrong, it's hard to sell somebody on, well, the fact that they're different is because it's now right. And so we've had to put in a bunch of work to add thresholds in. So like rate calculations, I mean, you saw some of those graphs. You say, well, we're gonna only compare the time windowed averages of these, which then that starts to look similar. You can't compare the raw counters coming off the devices because you get strange blips and defects. And so I think there was, at least early on, there was a big sales pitch to try to convince people that the data they were relying on previously is not accurate.
Thanks.
Any other questions? Sure.
Great, thank you very much.
Thank you.